In this video we'll discuss the importance of the sampling process, that is, how we extract a sample from the target population. The sampling process is a feature of the design of a study. There are many ways of sampling, but we'll mention only the most basic type, the simple random sample. And we'll try to show the connection of the sampling process with valid statistical inference. So you should understand that the aim of statistical inference is to make some statement about aspects of the population using a sample of observations extracted from that population. However, the meaningfulness and validity of any statistical inference from sample to population is connected entirely to this part, the sampling process. This can't be overemphasized. What this means is that really at all stages in the conduct of a study we're concerned with valid inference. In order to connect the sample to the population, we first of all need to understand what the target population is. Defining the research question will help us here. This is one of the most important first steps in research and comes down to a good understanding of what it is you're trying to do or what the research problem is. And I'm constantly surprised by how much time I spend in my collaborative work as a statistician trying to get scientists and clinicians to come up with a well-defined research question. If this is done appropriately, then not only will the target population be fairly apparent, but also the design of the study and analysis plan will fall out much more easily. So for example, if our research question is, does low-dose calcium supplementation lower the risk of preeclampsia in pregnant women, then the target population would be all pregnant women. Once the research question and target population are defined, and this usually involves a set of inclusion and exclusion criteria, we then have to be explicit about how we sample, how we select a sample, i.e. the sampling process. Here's a bad example of a sampling process, an anecdote. This example is taken from an honorary lecture that I attended at an epidemiology conference, and it concerns Winnie, a centurion who has smoked since the age of 7. And these sorts of anecdotes typically generate the type of inference along the lines of, well, my mum smoked all her life and lived to 100, so smoking can't be that bad. So let's put this anecdote in a statistical framework, as that's what this video is all about. So in statistical language, an anecdote is a solitary observation that is likely to have been generated by a sampling process that produces an extreme result. Or if it's a collection of anecdotes, a biased and unrepresentative sample of the target population. If it wasn't extreme, the anecdote is likely to be of little interest and you would probably not have heard of it. For example, no one's interested in Mr. Smith, who lived a life of moderation and died at age 79 of natural causes. It's not going to hit the front page of a newspaper. Now this might seem silly and obvious, but hopefully it makes clear the connection between sampling and inference. So valid statistical inference requires sensible sampling strategies. And anecdotes aren't just confined to newspapers. Here's an example published in a Lancet and later retracted. The study by Andrew Wakefield suggested a link between the MMR vaccination and autism, which led eventually to a massive drop in the vaccination coverage of MMR in the UK. And the actual study was a case series of 12 children with MMR and autism, which essentially amounts to a sample of 12 clinical anecdotes. And given how common this exposure and outcome are, it could have been investigated in a much more rigorous manner using a larger sample and more representative sampling strategy. The most basic method of sampling is the simple random sample, where each member of the population has an equal chance of being included. In theory, this would only be achieved by knowing our entire population and numbering them 1 to n, and then producing a random draw. In reality, we're rarely able to do that, so we often seek representativeness, which is often good enough. For particular research questions, such as those where we wish to estimate a simple descriptive characteristic of a population, for example the prevalence of a disease or the prevalence of an exposure, then taking a random sample is very important for minimizing bias and hence ensuring valid inference back to the target population. However, even when we have a perfect random sampling process to select study participants, we do not always end up with a random sample because of non-responders. In this situation, our study sample or analysis sample, which is those we analyse and whose statistical inference is based on, is different to our selected sample. People who don't participate or who participate and then drop out of a study later on are often, on average, similar in certain ways or certain characteristics. For example, the healthy volunteer effect has been noted in studies evaluating a screening or diagnostic procedure. These sorts of studies tend to attract more health conscious and healthier individuals, and thus the benefits of a screening program may be overemphasized. This is a form of bias called selection bias. Bias is defined as the departure from the true value which we are trying to estimate. In this case, the healthier volunteer effect is related to the self-selection of participants into the study. There are many types of biases that can occur in the sampling process, and we'll talk about more of these in the section on study design. So hopefully we've highlighted 3 important aspects of study conduct and design: formulating the research question, understanding the target population, and understanding the sampling process. So to help you navigate around these videos, here's a list of statistical jargon introduced in this video.